Okay, hello and welcome back to Old School Coding, where as usual I will be using tools from the 90s, a computer programming language from the 90s, and methods from the 90s to build a simulation of a microcomputer from the 90s. Sounds consistent, eh? So in the last session, we got the increment and decrement instructions going, both for the 8-bit registers and for the 16-bit registers. As usual, we are deferring operating on the memory at HL for the moment. And in this session, we need to start right off with seeking more things to do. Oh, and between sessions, I tidied up a little bit and got all the plots pulled together in the document file. So these, let me turn that off if I have just the text of it here. You see we've got our handy-dandy table of instructions that we will be filling out. That includes all instructions, not just the ones we've implemented. And it looks kind of like this. If we tell Emacs to show me those figures, there we are. So for instance, if we look down here, the test for INX, just as a quick example, we show ourselves executing a bunch of instructions, which we've got our data showing status, the instructions going by. We show the values being cycled into the 16-bit registers and being incremented. So for instance, BC starts out with this value AAFE, increments to FF, then increments to AB00, and so on for the rest of these. So we finished up the INR, 7 INR instructions, 7 DCR instructions, 4 INX instructions, and 4 DCX instructions. So for our next trick, let's see. I would like to continue focusing on the single byte instructions where possible. I will run the PDF forward to our big page and show it here. Whoops, not you. There. So where are some single byte instructions we haven't done yet? Well, things like exchange and, let's see, SPHL. These may be just miscellaneous instructions. Complement accumulator, complement carry, set carry. These are all kind of useful and just kind of scattered around. We have EI and DI. It's tempting to go grab the EI, DI halt package and say, well, we're going to do more, but that really is focused on the halt state and the interrupt control. So we'll just build a new module for single byte instructions that's just going to pull in the ones that I just identified. Move this out of the way. Beak. There. Okay, so we are adding a new module. Let's start right off here with I-8080 MISC. I literally am going to call this MISC. We may add instructions to it later. Now we'll use this guy to kind of inform how I'm doing things. So we do want to use this ret M1 for any of the instructions where it's the last T state. And we are basically doing a whole bunch of instructions that only have a T4. And the rest of that was all special stuff for halt. So this is how much I need to do for each instruction. I'm not sure I even need clock here. This guy will need clock because he's going to be doing things. We're getting away from using the static programs. And there we have it. Print top, print end, so we know that we are executing these guys. So now wherever I have ink deck, I want to put MISC below it. There we go. And now source i880.c. Wherever we have ink, we do a MISC below it. It's just the one. That works. And now when we compile, we see that we actually have an error, well, some warnings, because we are defining but not using a bunch of things. So that's good. So the first miscellaneous instruction, let me scan the table again. This is going to be SPHL, which actually has a T4 and a T5. But the T5 is going to be move something from the address latch back into the stack pointer. Let's start setting that up. Scanning the table really quick, are there any other places where we just have a final T state whose only job is to push something back into the stack pointer? We may want to share that T state. Hold on, stack pointer. Not seeing anything on the first sheet. Second sheet. Now, generally, when you're operating on the stack, if you are doing pushes and pops, it's going to be incrementing the SP during a T2 cycle, and it's got further work to do. So this is really the only place we're going to be doing this kind of thing. Okay. So what are the jobs we need to do for SPHL? It's really kind of simple. We're going to latch hold on, let me make sure I'm doing this in the right order. We need to take the HL register pair and latch it into the IDAL, the incrementer decrementer address latch. But HL, we don't actually have HL in our CPU model. We have H and we have L. No, let me just write that as a single expression. This is going to be CPU arrow H arrow value, cast it to word, left shifted by 8. All sorts of parentheses in here. C is famous for having slightly odd semantics on its operator precedence. So we take H, left shifted by 8, or it with L, and toss that into IDAL. Then down here in this guy, we are going to take IDAL and put it in the stack pointer. Let me update the stream description to say what we're actually doing while I'm thinking about it. We're going to do SPHL, and what else did I identify? XCHG. Let me see, are there any other? Okay, CMA and CMC and STC. And how about PCHL while we're doing it? So PCHL is conceptually a different kind of instruction from the rest. But on the other hand, it really is just moving a value from one register to another. So we're good. So there's SPHL. One by one, we resolve the warnings and errors. Now I'm going to pause here on the implementation because we have a new instruction. Let's go ahead and implement the testing for it. Now, what I noticed here is that we are not actually getting into these functions yet, so let's do that while we're thinking about it. Oops, misc. Post, and this is going to be reset for testing. This is really misc bist SPHL. So now we see we are getting into MISC post, and we're getting into it twice, and we're not getting into BIST. There we go. So we're getting into them. I can now delete these macros. And we're back to clean. And now I can implement the test for SPHL. These are all going to be small enough instructions. Let's just do all of this in one place. Let's not break it up into a bunch of subroutines. So test I8080 ink deck. We're going to be kind of like this. And I didn't write a bunch of comments between sessions. So the typical sequence that we were running before, we'll just grab this guy. And I'm going to use the same dodge I did before of forcing initial state into the CPU rather than writing a bunch of instructions to set it up. I do like the idea of beginning my test program with a NOP and ending it with 3 NOPs just to give us a little bit of margin on our plots so we don't start off with things jammed right on the edge all the time. I will tune the plots so that we do, but that gives us a little bit of leeway in case we want to expand it out a little bit. So the thing we're testing here first is SPHL, which means what I want to do is start off with data Z of H and L and adder Z. Actually, what I want to do is start off with everything set to Z. So there's all of the registers we care about. We don't care about A. We're not going to do anything with the accumulator this time, or the flags. We'll add those later if we need them. Now, since it's a BIST, we do have a tracing signal session. So our first instruction is a NOP. This is a 5 T-state thing. Remember, it's 4 T-states for the instruction, plus 1 because our ROMs are issuing a wait state. The other way we could do this would be to wait for the M1 ret signal to go high and then a few more. Actually, that's probably a better way to do it. So I'm going to add a little function here. And this needs to be specific to me until I make it global. Let's make it an I8080 function. I will push this out to the generic stuff, and this will be then living in my global namespace. But let's get it working here before I start using it everywhere. So we're going to do I8080 one machine cycle. At the end of that machine cycle, well, our first instruction is an op. Let's see. So what I want to put in the stack pointer is something that is distinguishable. So I'm going to start it at hex 7F. FF. You know what? No, let's actually use MVI instructions to set this up. MVI H L. Now, typically you don't set your stack pointer to that. I would set my stack pointer to one bigger than that. Yeah, okay. Let's actually do something that would map onto something more useful. Where's the top of the transient program area in CPM? Just to pick a typical value. Did I comment it here? Okay, so I could put it here at 2900H just to be absolutely typical. Let's put it at 2900. We're not going to be doing this under CPM or anything, but that would be a value that we might see in the stack pointer. So we want to assert that we see So we shouldn't have to assert these because we know those instructions are working. But I'm going to assert them anyway because if something breaks, I want this test to notify us that its preconditions were broken before it says that its results were broken. And now we do a plot. So I-8081 machine cycle hadn't been written. Let's write it. So what we're going to do is wherever we're starting from, we're going to skip forward as long as that M1 is 0. And then we're going to skip forward by the correct number of cycles so that we end up right on its falling edge again. M1 underscore int, right. I'm going to start off by asserting it. So if we ever call this and we are in that last T state, we haven't stepped onto the next cycle, it's not really clear what's going on. We probably didn't end the previous instruction properly. Okay, so the first time we call this, ret M1 is not 0. Oh, so this. And we do not want to, we don't want to crash out at this point. So source support.c, we're going to comment out that abort again. So what I'm going to do is I want to take a look at what's going on here before we start running our program. So let's run 90 clock cycles. That'd be 10 T states. Okay. So the thing is that when we start, I just realized ret M1 int is dropped to 0 at the beginning of the first T state of the cycle. So we cannot assert this. So what we want to do is, while it's 1, skip over it. Then while it's 0, skip over it. And that leaves us with a 1, so now we're going to say clock run to tau plus 8. I think tau plus 8 gets us there. Let's do tau plus 10 and see how many cycles off the end we go. Yeah, we're ready to do this. So it looks like we went one cycle too far. I don't want to see a rising edge on phi 1, but I do want to see it just barely not happen. There we go. So there's our NOP, runs to there. Then our move immediate into H. There's the H value showing up. There's the move immediate into L. There's the L value showing up. There's the SPHL, and there's the SP value showing up. So that works. Let's promote this I-8081 machine cycle to a standard bit of test code. I-8080 impl gets a declaration for it. That goes along with reset for testing as being useful. And we no longer have that. I'll leave the comments there because I did copy them in, but we'll delete them between sessions, delete comments that aren't useful, assuming I remember to do the patch up. I kind of jumped into it this morning instead of doing some between session things, you can tell. So this tests out and it works. So we go back into doc img, and there's our SPHL test. Just like we saw it before, we're doing the assertions and we're fine. So next instruction. SPHL is done. Single byte instruction, let's do XCHG. XCHG takes a single T state to do its job. It will need to hit M1 up here. And I will call it T4 just for consistency. So what XCHG does is it exchanges the values of HL and DE. I'm going to need a temp real quick. T equals CPU and H value data to okay, so there's the exchange instruction. Real simple. Let me make sure I'm doing the right thing here. I've lost it on the screen. There we go. So H and D swap, L and E swap, got it. So now we want to test it. So now we have values in HL. We want to do D and E are going to get something else. Just something distinguishable. I still have the values in HL, so now I can do XCHG. I'm going to toss a NOP in front of this. And in the end, when we're done, these guys should be exchanged. I am going to just use a single sig plot for all of this. So let's declare it up above. Oh, this is going to be confusing. I have a SP for stack pointer and an SP for sig plot. Call it sig P. Where I'm not using it as stack pointer, I'll call it sig P. I do need to declare it as sig plot, not P sig plot. So C has no problem with mixing things like that. So you can have uppercase SP and lowercase sp, no problem. But I like the telephone test, and if I say SP over telephone, I don't want to have to say, oh, this is this SP or that SP. Also means that if I'm reading it to myself, I don't get confused later on. So that does that test. Doc, image, exchange. So exchange, this plotted all the way back to T0 here. We want to start this exchange plot here. Let's do this again. So incoming, we already have values in HL here, 2900. We set up 3400, and then we exchange, and here's the correct values coming out. So this works. So just chunking through the instructions here. Let's see, the next one. Okay, so we have decimal adjust accumulator as a single byte instruction, but we have a number of other ALU quote-unquote instructions, rotates and so on, which I am not doing yet. I'll pack DA in with those. If I'm going to do that, is this where I want to go ahead and do those things? If it's not got an M2 or an M3, let's go ahead and do it. Yeah. INR, DCR, those are done. Inks decks are done. DAA. I'm going to defer DAA. It's a pain in the butt to test. Okay, so yeah, DAA and the accumulator stuff that goes neatly so elsewhere. I can put CMA, CMC, and STC in with that group. PCHL goes in this set. Now PCHL is, again, it's going to be like SPHL, except it's going into the PC. So downside here is this is going to vector my PC off to somewhere arbitrary. Yeah, so we're just going to have to set up a little bit of a program that runs at that arbitrary address. So PCHL T4 is going to take HL and toss them in the IDAL, and T5 is going to take the IDAL and put it to the PC and read M1. So we are going to write something into here. So test prog. Where do we want to send ourselves to? We are right now executing starting at 0, coming up through here. Well, you know, we could start executing at, say, the CPM entry point, which we will then have to put a little program at to capture it and say, yes, we got here. I am going to PCHL us to 3E00. And down 3E00, we're going to have the continuation of the program. So NOP 3E I didn't fix up the comments here. SPHL, XCHG, PCHL. I'm going to put it 3E03. hold on. Yeah, BIOS. So this will jump us into the warm start of the BIOS for CP/M. Well, hello, Lucy. Don't worry about the actual address. This is just to get us a typical address. And the thing we need to do here is also, when we set up our prog, so at this point, we still have our shadow line being used in our ROM select. So we have this one ROM that's doing everything, and it's masking addresses out, but this will be a distinct address. So here we're going to be testing the value of the PC before we start executing at that address. And I will put in 3 NOPs. Hold on. So look at who just woke up from her nap. It helps if I put the proper register name in there. Sometimes it takes a moment for the build to process it and get it around to where when we look at the log files, they've been written. But that looks like we are getting to the right place at the right time. Let's take a look at our image file. Come on. Doing this one-handed is a bit difficult. We need to look at PCHL. So, what have we got here? We should be seeing a NOP, which we do, 2 MVI instructions into various registers. So we set H to 3E and L to 03. And then we do the PCHL. And here's our PC setting set to 3E03, which we fetch from an increment of 04. And we get NOP, NOP, NOP. But the IR is set to FF because I didn't get the right thing, because when I mem copied into cells plus 3E, that actually copied well off the end of the array. Because, where did I set cells? Cells only has the memory for 1 ROM. So what I'm going to do there is I am going to just jump us up to 0, 1, 0, 3. So we skip the first 3. We're going to execute the second set of 3 in our test. More tests go here, and then we've got some trailing stuff. And 0, 1. Yeah, I'm editing code, aren't I, Lucy? So test conditions failed because I forgot to change the success value. And PC there we go. Okay, you're getting down. There we go. And there's our proper run that we see the PCCDEF 1011120103, which is where we sent ourselves. And we had some code we put at 0100 here, which is a bunch of NOPs, so we can see that we are executing NOPs at the proper address. So PCHL is now working. So we now have a way to branch, if we had to. EIDI halt are all set. So do I want MISC to include all of those ALU things? No, I want those to be in the ALU. So let's go edit the ALU implementation now. Yes, I know this is already pretty big. But what do we have to do for these? Well, DAA, let's at least set up the decoding for DAA. This, like this. So, definition of DAA. Let's bring our PDF in. We need to do this sometime. I might as well do it now. Where to go? DAA. The 8-bit number in the accumulator is adjusted to form two 4-bit BCD digits by the following process. If the value of the least significant 4 bits of the accumulator is greater than 9, or the AC flag is set, 6 is added to the accumulator. If the value of the most significant 4 bits of the accumulator is now greater than 9, or the carry flag is set, 6 is added to the most significant 4 bits of the accumulator. Let's move this out of the way again. And I believe, well, we'll check and make sure this is happening in the right place. But this is an honest state T4. This isn't one of these T2 things. So I want to put it kind of at the top of the implementations. Yeah, let's put this at the top of the implementations. In fact, I'm going to pretend that we implemented this first. So it's going to go at the top of the static functions and all of that. So it is indeed a last cycle. Oops, I do not need to do that. So ALU is equal to, oh, not ALU, this is AREG. Just call it A. So if the low 4 bits of A are greater than 9, or CPU flags value amper then A plus equals 6. And this does say all flags are affected. So what I'm going to do is I'm going to do all this with a single add so I can collect the half carry from it. Okay. Now I'm going to have to do something a little weird. So we're going to just compute the thing. Now the top nibble, if it is greater than 9, or the carry flag is set, okay, and what I want to do is carry this sum as unsigned. So we're going to extend that and carry a whole bunch more bits. So we can get, this is so we can get the carry bit out. This may have a carry out. And all flags are affected. So now we need to know I'm going to look at the path, see if this is actually just going and operating directly on the accumulator. It can't be. So according to the T-state layout, DAA, DAA is a register apparently, according to this, because it just says DAA into A in flags. So there may be a separate register that gets the decimal adjusted thing when the ALU operates, so that later when you do a DAA, it just goes into place. Which means all of the add ops and sub ops need to set this DAA. Oh, no. Not going to model it, because that would be a lot of extra work and every ALU, every arithmetic operation. I mean, we're already going to the effort of extracting the half carry. And during my early career, I never really professionally programmed on the 8080. By the time I was doing anything professional, it was on mini computers. I started out on DG or working on Unix, on Suns, and so on. So this may not be fair to state, but in my hobby work, I didn't notice people using DAA all that much outside specific games where you are tracking a score to be displayed and you just use decimal math for it. I suppose, yeah, okay. So I could see why maybe the 8080 pre-did its decimal adjust and got it all working and had a DAA register that you could just latch in, so that the decimal adjust accumulator actually takes 4 T-states, whereas things like increments and so on take more. So you didn't really have one cycle to read A and another cycle to write. You just wrote DAA into the A register, so we'll just pretend. So the half carry, we had a half carry if ACC amper 15 is less than ALU CPU. Actually, let's have ALU and DAA here. What do you mean used but never defined? Oh. DAT4. Gotta love transposition of characters. So what I want to do is synthesize some decimal adds and verify DAA does the right thing. And I am going to leave that as a to-do item because that's just going to be a grind. In fact, I am going to insert that at the top of this. So we'll test DAA before we test, oh, wait a minute, that goes in the ALU testing. I'm sorry, I-8080 ALU test. So we have a to-do to build some DAA tests. Let's put that in the README. Now, I do want to have at least a little bit of testing here. So in MISC test, I will add no, I do not cross this up, Greg. I keep doing this. I-8080 ALU test.c. I need to just write something here. So down below CMP, we're going to have a DAA. And what I'm going to do is do this completely in A and C. And let's set up at least one test that does something that will trigger DAA. I'm going to cause it to do the whole thing, so we're going to add OX66 to OX55. Okay, that'll trigger both of those conditions to occur. And we haven't refactored any of that yet, but we're going to go to pick it up from MISC now. So one machine cycle is what we're going to do. So NOP, MVI AX66, MVI C55, add C, DIA, nop, nop, nop. Don't need to test that. What I will do is I don't know what the flag is going to be here. Let's find them out and decode them and so on. But I do know that 6 plus 5 is 11, so that's 1 carry the 1. This is OX, should be OX21 is what should appear here, if I've done it right. Unused variable C. Right. So this is saying we expected BB, which I got was 102 in the accumulator after we did an add C. Let's see, NOP, via A66. Oh, this isn't one machine cycle, it's one instruction cycle. To do. Rename. Just to make sure I'm getting what I think I'm getting, let's assert that A is set to 6.6 here, and C is set to 5.5, and now we need C. So A and C are being set, and I'm issuing the add, and I'm not getting the right value, because that value is delayed by 2 cycles. So clock run until tau plus 9 times 2. Almost forgot that. Well, did forget that. So flags, this is saying that the flag value is insert format 134 is 86. This is S because we're negative, and P and half carry is not set. That's correct, but we are greater than 9. So this is a decimal adjust without worrying about the half carry. I do want to worry about the half carry, so let's do 8. Let's do a 9 and 8 here. So my sum is going to be 98 is going to be 1, and 65 it's going to be C1, and after the decimal adjust, it's 9 and 8 is 17, carry the 1, 6 and 5 is 12, it's 11, 12, so 2, 7. So now this is saying that the flag word is 85. Oops, is it? No, it's 134. Oh, right, we got an indent ran through here, changed our line numbers. So C1 is actually getting back 187. Yeah, it helps if I actually change those values. Oh, come on. I probably should make just normal definitions rather than keyboard macros for copying observed values in. I keep thinking I don't do it enough to warrant it, but I do actually do it enough to warrant it. So is that correct? 9 and 8 is 1, carry the 1, 6 and 5 is C. Okay. 6, this is now 246, which is 92. 92 is S and AC, and that's it. Then we DAA, and the result that we're going to get in the flags is 7. Seven is P and CY. So that's correct as far as I can make out. I don't see that anybody would want to use the half carry, the auxiliary carry, after DAA instruction. It would be set pretty much any time we added that 6 in. That was the whole purpose of it. But you wouldn't want to do a DAA followed by another DAA, right? So that's not a complete test of DAA, but it does verify that the instruction is there and we're actually exercising the data paths. Okay. Next instruction, looking for more 1-byte ALU-ish, which are going to have ALU results written back in the second clock. Second sheet. Okay, so this looks like I need to skip down to the rotate instructions. There's a whole bunch of them. I'll just do them all kind of blasted together. RLC, RC, RAL, RAR, CMA, CMC, and STC are all ALU kinds of things. What else might we have? I think that's all I want to put in here. So the places I do DAA, I need to do the rest of this stuff too. So keyboard macro I8080 underscore state underscore. Grab those three. That was a fail. Okay, so I8080 underscore state. Okay, skip down to DAA, and below it we're going to implement these functions. Oh, they're all going to look very, very, very familiar. There's a bit of code that they are going to execute inside Phi2, which is going to be unique, but the rest of it's all boilerplate. So I can use a keyboard macro to do the work. Let's write the first one, and then I will duplicate it and make it do the other ones. So start off with this body, and I need this. This is RLC. So definition of RLC. I am going to change my PDF viewer to one page and bring it up so we can look at the definition cleanly. Okay, there we have it. PDF into OBS. Bink. Toss that over on the left, and I'm going to bring it in front of my camera. And let's actually increase the size of it. So RLC is rotate left, so the bits of A left shift by 1, and A7 goes back into A0, and A7 is copied into the carry. So this is not a rotate through the carry, it's a barrel rotation of the accumulator, which also sets the carry. Got it. Now, is this supposedly happening all in one single T state? Let's go back to the table. So RLC, so what this states in the table, let's actually show it on here. So during the T4, A goes into ALU and we rotate. And then the M2T2 ALU goes into A and the carry is committed. So RLC T4 and RLC T2. The T2 guys just look like that. So I'm going to borrow him. They're only called during one particular phase of the clock, so we're good. And this is a generic, no, we're actually doing the rotate here. Okay, we're good. It really does say to the ALU and rotate. But I do need to carry the flag down. Yeah, I need to do the rotation in the T2. Yeah. How about this? We'll move to ACT. So we have ALU, we have ACT, ALU, and then we'll have to grab the flag in the other half of it. So ACT, CPU, arrow A, value. So data to A from the ALU. I almost need to carry the ALU as a 16-bit value so I can get that carry out there. But then what do we do when we're doing a right shift into the carry? Okay, question. What flags do those actually hit? Only the carry flag is affected. Haha, I could do this the easy way. No, let's not do it the easy way. Let's do it the clear way. So all of these guys, not all of them, some of them, do these one instruction at a time. I'm going to do a test here for all the rotates. Let's call it rot. We're going to do 2 rotates, so we should see that pattern do something interesting. Let's do 5F. So 5F rotated left by 1 would be 1011, which is BE. And that rotated left again. Oops, hold on. 5F is 0101, 1111. Rotate it left, we've got that. Rotate that left, we've got that. So 5F goes to BE, which goes to 7D. We do need to get things in the we're going to do an XRA, A, to get known state. Clock run until don't you see in this test yet? So we actually saw 70. So 4.6 is the thing we're familiar with. That is what we get for 0. Which is Z and P. And these flags, we move it there. This should still be 4.6. And this should be 4.6 because we do not have carry yet. And this is 71. Which is Z and P and CY. So that checks that the value is rotated properly and we get the carry set at the proper time. And this is not DAA, this is ROT. Actually, this is RLC. So, there, we are zeroing the accumulator. Boom, there's a 0 in the accumulator. And then we move 5F into it. There's 5F, RLC, RLC, and NOP. (5F BE 7D). We're seeing it. ALU is picking up the BE and 7D at the right time. The accumulator temp is getting the inputs, so 5F to BE, BE to 7D. And the flags are sitting at 4.6 until they become 4.7. So this is a good diagram of RLC. Next instruction. RRC. RRC is just like RLC, except it goes to the right. And I picked up an extra chunk of stuff there. There we go. RLC T4, T2, RRC T4, T2. So the implementation is now ACT left shift by 7, ORed with ACT, right shifted by 1. And the carry flag now comes from the least significant bit of the incoming accumulator. And now we want to test this with a FA. So FA rotates to that, which rotates to that. So FA becomes 7D, which becomes BE. And we have the carry appearing during this cycle. This is RRC. The SP is being reused, so we'll declare it up here. And we actually saw 245, which is F5. I wonder. Well, ACT is defined as a word, so this should work. Now, I'm going to write it that way just to make it more clear in my head what's going on. Be nice if my observed values and expected values were printed in hex. So here, we're running the machine cycle and then 2 more, and A is not getting the proper value. Also, this is the wrong carry flag. There we go. So if We had an 8-0 in the accumulator when we started, then we'll set the flag. Watch me be something simple like off by 1 on my instructions. How about I don't do the XRA in the second set? Let's just do a NOP. Oh, we didn't do the, yeah, we did step over the NOP there, so we're going to need another NOP. So this is setting the carry again, even though we are doing a, oh, there we go. And we should do the XRA up here to get into a known state. So now, this guy is saying we're actually a 47. Which we shouldn't be. We should be a 46. So rotate right circular. Old A0 goes into carry. There we go. Rotate left circular, the old A7. Good. This is why we test in detail. So now that's correct. Let's take a look at the plot. Taking a look at the RRC plot, and here we are. So we see A gets cleared, set to FA. FA shifts to 7D, there's 7D, shifts to BE, and we get the carry out as the 1 bit goes off the right-hand side, and there's BE. So RRC is done. RAL. Just like RRC. So RAL, definition of that, rotate left through carry. So we rotate left, we shift left the accumulator. The carry, A7 gets copied into the carry, and the carry gets copied into A0. So more complicated. So the ALU is equal to ACT left shifted by 7, ORed with the old carry bit. And we know that the carry is in the least significant bit, so we don't need to shift that around. And down here, it's going to be the top bit that gets copied in to the carry. well, the old top bit. I'm going to do the same thing with RLC. So RLC gets made into RAL. This time I am going to do three of them so we can see the end-around carry effect. Okay, I will just run the test to collect the results. Now, we expected BE, we got 8.0. Well, that's complete garbage. That's because I left shifted it by 7. 1 is correct. There we go. So, take the 5F with no carry, and we shift it left 1. So, have the carry bit out on the right here. Did it too soon. I need to do one more cycle of it. So there's our result pattern. So we started off at 5F with no carry. We left shifted at 1 and we get BE with no carry. Left shifted again and we get 7C with a carry. We do it again and we get F9 with no carry. And that worked. This is RAL. We see the same pattern here. So accumulator temp gets the value, and 5FBE, BE7C, 7CF9, we get the carry bit going on and off. We get IR with our instructions. We see we got a couple of 1.7s, three RALs in a row. We're not putting a vertical bar in there. That's correct. So RAL is now working. RAR is just like RAL, but the other direction. careful that I don't mess this up again. So RAR puts the carry in the top bit of the accumulator and takes it from the bottom bit. So this guy needs to left shift by 7, forward it with ACT, right shifted by 1. And down here, it's 01. So RAR is just going to be just like RAL. Well, it'll be just like this guy. I'm going to toss in an extra 1. So like RRC, except for how the carry manipulates. I didn't fix the comments here. This is RRC. So RRC, our initial value is FA. So we're going to put the carry at the top. So carry is initial clear, then FA. It's RR, so we are going to take all but the last one and do that. So FA becomes 7D, which now becomes 3E with the carry set, which now becomes 9F with the carry clear. That's RAR. How about that? I typed the numbers right the first time. There's our RAR plot. Looks just like the others. FA 7D, 7D, 3E, 3E, 9F. So we saw the right stuff. We saw our carry going on and off. And this looks good. RAR is done. CMA. CMA complements the accumulator and does not touch the flags. And it is here. So the whole thing happens in T4. I'm going to make it look just like this. Red 1. And we literally are just going to say So what I want to do here is op, nop, op, MVI, AOX. Let's do 5A. Let's make something so that rotating it wouldn't do it. Let's do 5B. CMA twice, and NOP. We don't worry about flags on this test. 5B inverted is going to be A4, and complement again is going to be 5B. Result appears immediately. These aren't used. What did I do wrong? I put it in ALU, I didn't put it in A. There we go. Yep, inverting the wrong thing is a bad idea. Okay, that's correct. Let's see if the plot looks good. This is CMA. So D, 9F, 5B, A4, 5B. So 9F was our incoming value, and we smacked it. CMC complements the carry. So this is just like CMA, but it's going to do something different. CMC literally inverts the carry flag during T4. Really simple. So the test for this, we're going to do an XRAA to clear everything out. We're going to complement the carry twice and NOP. So carry flag is in least deviant bit, so we should go to 4.7, back to 4.6. Well, hell, accumulator is getting 0. Oh, okay. And now test the plot of that. So complement carry should be manipulating the flags. Get the ALU to 0, accumulator temp, data, data, data. All this stuff is crap. And accumulator is 0 here. So we do the complement carry, goes to 4.7, goes back to 4.6. So CMC is working. Yay! We are making steady progress. STC sets the carry. So if we do it twice, it should be idempotent, right? Okay, so CMC, anything that is CMC, we're going to make a STC out of it. There we go. Real simple. And that worked. STC is down here. We see that the flag turned on and stayed on. We see that the test says it turns on and stays on, and we're good. Okay, so we have added a whole bunch of miscellaneous instructions, which included the ALU rotate instructions and the other miscellaneous things. Those actually would appear as basically this column right here: RLC, RRC, RAL, RAR, DAA, CMA, STC, and CMC. We have a big to-do item for a complete DAA test, but we have something that triggers the code to run, which is good enough for me for now. If I were trying to produce this for a real simulator, let's say I was working at a small microcomputer building company back in 1988, and I was doing this to try to simulate the system we were building, I would probably do a lot more in-depth test vector design. We might take a couple of weeks just to design test vectors. But for what I'm doing here, knowing that it's basically working combined with the fact that I know my host system is working properly, I don't have to do that. Are there any other of the single little bitty instructions that I haven't done yet that I can drop in here? Well, we've got all the immediates here. Same thing as what I just did, but now, no, I've already done those. Have I done those? No, I haven't. I did add, I'd have the add, subtract, ADC, SBC, and so on set up, but I don't think I did the immediates. Okay, so maybe that's the thing we do during the next session. This is getting on into me needing some lunch. I'm going to break for lunch. Maybe I'll come back and play some computer games because I'm kind of 80-80'd out at this moment. But it looks like our next thing is going to be to start working on things like the ALU with immediate operand things. It's in and out, could be interesting to get done at this point. I don't want to get into the ones that take 16-bit operands quite yet. I don't want to get into the M stuff quite yet. We'll see what shakes out. Could be interesting to add some code to our simulation that will actually print the list of opcodes that it has not yet implemented. Oh, let's do that now. Yes, that would make sense. So, that's going to require a couple things. First of all, in 8080.c, we do all this initialization, and we call all of these guys that say, set this stuff up in linked I8080 report unset. I need to put that there. There we go. So I'm going to do a couple things here. First off, I'm going to initialize these guys, well, the tables. Which ones do I want to report? I want to report just M1T4 that is not set. So the easy way to do that is if it is set, continue, set it to power on and print something here. And then over here, I'm going to say null. Comparing versus null is very well defined. So we now need a function called I8080 instruction name, which gets us the names of all of the instructions. Yes, this is going to be automatically generated. Oh, I can turn off the PDF in the OBS display, can't I? There we go. Implicit declaration of instruction of function should be, oh, right. So I can either generate this from Python or I can do it by hand from the opcode pound defines that it turns out. I think I like doing the second one. So it'll mean I'm maintaining C source here. I8080.h since I'm not actually running Python to generate these, no, let's generate it from Python. Getting them in the right order might be a pain. Gen opcodes.py. So CSTRI I'm using the F string with the triple single quotes here in case I want to do other things, but I just realized that's going to cause problems because I am not actually making use of it, and it causes more problems when I try to print the brackets. Okay, so it's for op. So what I want to emit first is a table. Followed by the function. And you could probably see what the function is going to be very quickly. Okay, so here's what that Python code now turns out. It gives us our nice opcode table. It provides our pound defines, and then it prints all of this stuff. I'm just going to grab this. And that goes right in here. And what I'd like to do is make this table a little nicer. Yeah, I'm about to replace it. Okay, so I am Not quite there yet. There's the table. Now that does mean my disassembly is going to have a whole bunch of blank padding, so all of the op names that I print are going to be the same length. I kind of like that, and I can always do something different if I need to. But for now, we're just going to go with this. So there are all the operations that we know about. And in I8080.C, we've got that. And now we go back up to the top and expected something here. Well, I forgot a semicolon, right? So indent messes up this table. Can I narrow it? Well, I want 4 for the opcode, and I want these guys to be wide enough. I could tell indent to make my lines longer, but then it would reflow everything else in the system. Yeah, let's make the table half width. Still decent enough. So we're going to do this if M1T4 is set to null. And indeed we are. So we're not actually calling report unset. Well, we should be calling it. Are we actually getting there? Counted 0, so they're all being set to something non-null. Well, I'm supposed to be setting them to null here. Okay, so this is telling me that these are in fact set. And it would be interesting to find out what they're set to. It's too bad that looking things up like that wasn't built into the C programming language from the beginning. Debuggers are an add-on. If this is NOP, this looks like NOP. In fact, it looks like pretty much everything is being set to the no-op value. So who's messing with it? M1T4 of inst is equal to null. Looking for anybody modifying M1T4 in the CPU. We're doing it with specifics here. So this is specific to this set, so 80 through BF, that's correct. How about I don't ignore case? EI, DI, halt. Oh. This is an old thing. The opcode, decode, table is initialized. The caller to carry break me hard kill sim content. That does mean I need to make sure to set it in cases where I wanted to go to the X. This may mean I'm not hooked up to X for anything yet. So if I scan over here, I can look for op-nop, and I see it's not there. So what I can do now is say M1T4 op-nop is equal to I8080 state X. So at this point, it looks like fetch is now owning the no operation code. Okay. So yeah, we weren't actually explicitly recognizing no op, but now we are. If I eliminated this here, I could eliminate that. Now let's not eliminate it. Let's actually formally say that this owns that and state X is really state NOP. Are we good? So this complains that the argument type is not proper. This complains that ISO-C doesn't allow me to print a pointer to a function using %p. And we now see that we have a bunch of nils, so I am going to wipe out that like that. And here are the things that we haven't done yet. In fact, we're going to relegate this to the BIST section. So at the end of BIST, no, this needs to be done every time. This part needs to be done every time. So what we're going to do is we need to use this same power on thing elsewhere as well. So, yeah. You know what? This is too much sugar for a nickel. There. We'll just have to remember what we haven't done. And I could check it from time to time, but we need to use state power on to initialize it. If we print it, we'd want to print it from here, but we'd only want to print it during BIST. I don't know, maybe we just have a bit grid that pumps out or something, I don't know. Maybe we add that as a test later on and have a callback into 8080 to find out whether it's a legal instruction or not. There are some illegal instructions. Maybe we lock down one of them as being the illegal instruction. Maybe we put power on in the CPU. I don't know. But it looks like we're there. So I'm going to end the stream, and I will brush up tests and finish up comments between sessions. I'll see you in the next one. Meanwhile, keep it small, keep it simple.